and gentlemen, welcome to the final session of the International Robotic Sailing Conference. I'm Paul Miller back again, and it's my pleasure to introduce Roland Stelzer. And I saw Roland's paper as one of the anonymous reviewers of Roland's paper. I guess I'm not so anonymous anymore. I was the one who said, this is a great paper. It's a very interesting paper because, for me anyway, over the years I've always wondered what is the potential energy savings from balanced strait. Roland's going to answer that. Roland mentioned to me that if there are any really tough questions, he's going to dodge them because this was actually mostly written by one of his graduate students, and so he can pass it on. Roland, thank you.
Thank you very much. Yes, that's true. A lot of the work I will present now has been done by Daniel. Daniel was on a 6-month internship at our institute, and is from Spain. And he wanted to come here, but Spain is out of money, and therefore he couldn't afford to travel here. That's a pity because he is really the expert on the simulation behind the simulations. But I want to try to give you an impression of why did we compare some rigs, and what is the outcome, and what does it mean for our boat. For those of you who doesn't know me and our boat, this is our boat. It's the first time that I'm on the World Robotic Sailing Championships without a boat. It's because our funded project ended last August, and it's always the same, it's a matter of money. The boat we use is of the boat type Lehrling. This is a little keel boat with almost 4 meters in length, 2 sails, loop rig, and yeah, solar powered, and so on and so on. And the last mission we did, it was in July in the Baltic Sea. We tried to find harbor porpoises, and had a mission from Eckernförde, north of Germany, to the north, to the little belt in Denmark and back, and it was autonomous sailing for about a bit more than 70 miles in winds from Beaufort 5 to 7, and we were surprised how well it did, although we have seen that some improvements, especially on the rig, are necessary, especially with focus on power consumption. And power consumption, this is the problem, one of the big problems we have. We have solar panels, 1.5 square meters of solar panels on top of the boat. This provides 285 watt peak. What is in Central Europe, about 10% of the watt peak is what you can get on average over a year, day and night, so about 30 watt. But the consumption of our system is about 35 watt. That's pretty much compared to some systems we have heard this afternoon. And it's much, and there are possibilities to come down significantly. We did not focus on power consumption at all so far, because what we wanted to have is a working artificial sailor. Our focus was on algorithms and on imitating a sailor's behavior on a computer. And now, when we start with real-world applications, we see, okay, now it's time to reduce the power consumption significantly. We have a negative energy balance, although we were able to do, we are able to do missions of several days. Because of this is a direct methanol fuel cell, which automatically switches on when the voltage drops below a certain threshold and provides enough power. You can attach a methanol tank available in different sizes, from 5 liters to 28 liters. and with 35 watt power consumption, you need about 1 liter of methanol to sail a day, if the solar system would fail completely. So with a with a big tank of 28 liters, you could sail about a month. Yeah, but 35 watts is too much, and therefore we thought, what actions can be taken to reduce the power consumption? And what we see here is that with 44% of the overall consumption, the computer is the consumer number one in our system. This is a very, very old standard PC running Linux, and we took this computer in, I think the computer is from 2002. We took this because it was very comfortable, a lot of interface, a lot of computational power, at least for that time. But it needs or uses a lot of energy. But you can replace it easily by a more modern embedded system with comparable computational power, and come down easily from 15 watts to 3 or 4 watts. So this is not the big problem anymore. Then we have a lot of sensors on board, some of them redundant. There may be arguments for redundant sensors, but they are not necessary if they do not fail. So if the goal is really to come down with the power consumption as much as possible, you can discard the redundant sensors, and the only sensor we need is the PV200 weather station, which combines wind sensor, compass, GPS, tilt sensor, all the sensors we need. In fact, this is the only sensor we use on the boat for now. Then we have various different communication channels available for tests close to shore. We use Wi-Fi. Then we can use a 3G link also close to shore. But for long-term missions and open water, this is not necessary. And yeah, if I just use the Iridium modem to transmit data whenever it's necessary, it comes down. But the biggest problem, where it's not so easy to reduce the power consumption, is the sail gear. And once again, we have seen in the Baltic Sea that, especially when there is a lot of wind, this is power consumption on the sail gears is too much. So, and our goal is to come down to 50% from the actual power consumption, which is on average 4.5 watts. Does not mean that the sail gear does not consume more, because most of the time it's passive and it's not working. So this is every 10 seconds it readjusts the sails, and even then it's more than 4 watts what it consumes. Why do we anticipate a decrease by 50%? We did the same with the rudder. We had a rudder with a tiller and a tiller pilot, or the tiller pilot was actually the same linear gear you use inside of your boat now, and replaced it by a balanced rudder where the motor is directly attached to the rotation axis, and we have now a consumption of minus 97% in comparison to the old system. It's not just because of the balanced rudder, it may also be because the new motor is more efficient or so, but mainly because of the balanced design. And therefore we think the same should work with the sails. Of course it does, but we don't know whether it's really worth to try, whether it's a really significant difference. So a balanced rig, Paul has mentioned it before, means that both sails, the mainsail and the jib, are on a single boom, which is rotating, and if you tighten the sheets, you don't need to act 2 times against the wind force, but you have a counter force from the foresail, and the overall torque is reduced. Yeah, here are some examples. I will add the photo of your boat later. This is the boat from Yves Pierre, who is not here today, unfortunately, or this boat we've seen just before, the Weimos, and also a balanced rig, but not a Baltron rig like these two, is the Avalon from Zurich. I think they are currently trying a new several days mission. I wish them good luck. Yeah. And so, what was the question for our work? Is it possible to save 50% of power on the sail gear? It's the first question. The second one is, how does it affect the sailing behavior, or does it decrease the sailing performance significantly? And the overall question is it worth to try for us? And these are the 2 designs we have compared, and because we don't want to waste a lot of money for this try, we tried to keep most of the parts identical in both designs. So we use the same sails, we use the same mast, everything is the same, except that here we have this boom, typical for a Baltron rig. And then we did CFD simulation, and this is the part where I cannot provide that much details because this was done by Daniel. But as mentioned, mast height, sail area, and sail shape has not been modified. What we did in our simulation, we tested several points of sail, several angles to the wind, from close hold 30 degrees to the apparent wind, to 180 to a downwind course in steps of 15 degrees. And we always positioned the boom in half of the apparent wind angle. It's an approximation because we don't know exactly, it's not so easy to determine how our boat and our algorithm sets the boom in certain conditions. But this is an approximation to have half of the angle for the boom. The sail shapes have been defined according to an article on this website. It was the only and first I found, and I hope that these guys did a good job. So this was where we found our sail shapes for the simulation. The 3D model was made in Rhino, pre-processed in ANSYS, and the CFD simulation in Star CCM. Yeah, for those who are familiar with the topic, they may know more about this. I'm not an expert in the simulation. This is on the results. On the left-hand side, we see the sail torque. The sail torque for both rig designs, and it's pretty much the same of all points of sails for the unbalanced rig, the same for the balanced rig, but significantly lower. So on average, over all points of sail, you can expect a reduction of torque of 68%. Of course, this does not mean that the power consumption is minus 68%, because the efficiency of the motor and the whole system is never 100%. But that's the torque you have to act against, and this 68% makes us quite optimistic that we can reach the goal of 50%. What does this mean for the sailing performance? I know I'm not a naval architect, and I know that sailing performance is a very, very complicated field and can be described by many parameters. We investigated just two of them, the forward force and the lateral force, and the ratio between those two. And what we see is that the forward force for the forward force is higher for the balance rig. It's not a big surprise. If you imagine a downwind course, then usually with a sloop rig the jib is covered by the mainsail, while with a balance rig design you have the full sail area where the wings can act on. Therefore, especially for downwind courses, it's a big difference, while the lateral force is comparably not a big difference. Yeah. And so what we can say is that the sailing performance data, the forces, forward force on the boat and lateral force, are not significantly affected, or at least not negatively affected by the balanced rig. And so what are the conclusions? The conclusions are that substantial saving of energy can be expected. There's an X missing, and there's no negative impact on performance been identified. And so the real conclusion is, for us, it's worth to try it, and we will try it as soon as we have the money to build the new rig. Thank you very much.
Question for Roland. Of course I have one. And you may pass this off on your student. In the CFD analysis of the sails, did that include the viscous separation effects?
That's one of those
Questions. Okay.
I'm sorry.
Oh, no, that's fine. And the second question would be, so the sails he modeled were the two sails straight off the boat.
Yeah.
And in the case of the jib, he moved it up.
Yeah.
So does the boundary layer, the fact that the sail is now in more wind, figure into the results?
It did, but we did not investigate this effect separately.
Okay, great. Does that spur anyone on for an additional question? No. All right, Roland, thank you very much.
You're welcome.